Have you ever really stopped to think about what's going on inside, the digital devices you use every day? Your phone, the servers running the internet, it all seems kind of magical, right? Just works. But underneath all that smooth software, there's this fundamental hardware choice being made. And that choice shapes absolutely everything. So today we're doing a deep dive into that hidden world. We're talking field programmable gate arrays, FPGAs, application-specific integrated circuits, ASICs, and systems on chip, or psychics. Now, these aren't just random acronyms. They're basically the three main ways digital hardware gets built, and each one has its own personality, its own pluses, and definitely its own trade-offs.
Exactly. And that's our mission for this deep dive, to really pull back the curtain on these architectures. We're going to look at how they're fundamentally designed, how they're actually manufactured, and then really get into those critical trade-offs, things like performance, power, how much space they take up on the silicon, cost, and how quickly you can get to market. And the key thing to grasp is that there's just no single best answer here. It always depends on the specific job you need it to do.
Right. So if you want the inside track on a really critical part of modern electronics, the stuff most people overlook, but that's totally fundamental, then you're in the right place. We think you'll find some surprising stuff here, some really practical insights. Let's dig in. Okay, let's kick up with FPGAs. I kind of think of these as the chameleons of the chip world. They're super versatile. You get hardware speed, but also a lot of software-like flexibility. But the real defining thing about them, the standout feature, is that you can configure them, even reprogram them after they've been made. We're talking actual in-field reconfigurability, which means, you can adapt to new standards, fix bugs, add features, all without having to physically remake the chip. That's huge.
It is huge. And if you look inside the basic architecture of an FPGA, it's essentially this grid of flexible building blocks. At the core, you have what are called configurable logic blocks, or CLBs. These are the basic programmable units doing the actual logic work. Inside those CLBs, you've got lookup tables, LUTs for combinational logic, and flip-flops for handling sequential stuff like memory. Modern FPGAs just pack these in incredibly densely. You might have CLBs with, say, multiple 6 input LUTs and flip-flops. It allows for really complex designs. And crucially, connecting all these CLBs is a really sophisticated network of programmable interconnects. It's like a programmable wiring system. That's what gives them their flexibility, allowing you to connect the CLBs in almost any way you need. Then you've got the input-output blocks, the I/O for talking to the outside world. And beyond that, many FPGAs now have specialized hard IP blocks built in too. Things like digital signal processing elements, DSPs, which are really important for AI and radio stuff. Plus embedded memory blocks, block RAMs or BRAMs, and sometimes even entire CPUs embedded right there for system control. They're really quite powerful platforms now.
That flexibility really is key. So if it's so reconfigurable, what's the design process actually like? I've heard this term high-level synthesis, HLS. Does that play a big role?
Oh, absolutely. HLS has been a real game changer for FPGA design. Traditionally, you'd use hardware description languages, HDLs like VHDL or Verilog. Very powerful, very precise control, but they're very low level, almost like, writing assembly language, but for hardware. It takes specialized skills. HLS tools from companies like AMD with Vitis, Intel with Quartus HLS, Synopsys, they let designers use higher level languages, think C, C++, OpenCL. But what's powerful is that these tools abstract away a lot of the low-level hardware fiddling. They automatically translate that high-level code into hardware logic. This really opens up FPGA programming to more software engineers, people who aren't necessarily deep hardware experts, and it speeds things up massively, especially for fields like AI where you need to iterate quickly.
Okay, so FPGAs give you that amazing adaptability. But what if adaptability isn't your number one priority? What if you need just raw absolute efficiency for one specific task? That sounds like where ASICs come in. These are the meticulously crafted specialists, right? Custom chips for one fixed job. And once they're made, that's it. No reprogramming.
Exactly. That's the heart of the ASIC proposition. Maximum efficiency for one specific function, period. Because it's custom built, you get the best possible performance, significantly lower power consumption, and a smaller physical chip size. And if you're making millions of these things, think high-volume products that custom optimization makes them incredibly cheap per chip. The upfront design cost, which is high, gets spread out. Think about your smartphone, and again, every tiny bit of space, every milliwatt of power matters intensely. ASICs deliver that. They're literally designed transistor by transistor for that one job. That's kind of the secret sauce enabling today's incredibly compact and power-efficient mobile devices. Now, how they're made, there are a few different approaches, each with trade-offs. At the top end, you have full custom design. This is the most complex, most expensive, Every single transistor, every wire is handcrafted for peak performance and minimum size. That's how things like high-end microprocessors get designed. You're squeezing every last bit of performance out of the silicon. But the cost, design, and manufacturing are huge, and the lead times are long. Manufacturing alone is maybe 8 weeks, and that's after the long design cycle. Then you have semi-custom designs, which try to speed things up. One type is gate array based. You start with pre-made arrays of transistors, and the designers just define the connections between them. Faster design, but not quite as efficient. The most common approach today, though, is standard cell-based design. Here, you use a library of pre-designed, pre-tested logic cells like basic AND gates or OR gates, flip-flops. Think of them as pre-approved building blocks. You pick these cells from the library and arrange them. This massively cuts down design time, cost, and risk because you're using proven components. It's the workhorse for most ASICs now.
That's a really clear breakdown. Okay, so from specialists to, well, systems on chips, SoCs, these sound like a whole different beast, like a paradigm shift almost. Taking most, or maybe even all, the major parts of a whole electronic system and cramming them onto one single chip.
That's the idea, yes. It's a highly integrated approach, and it brings some really compelling advantages. First off, power consumption generally goes down significantly. Why? Because communication between chips is surprisingly power hungry. Keeping it all on one chip saves a lot of energy. Second, the physical size of the semiconductor die area shrinks dramatically. That's absolutely essential for small devices. Smartphones, wearables, IoT gadgets, they wouldn't be possible without this level of integration. And third, latency drops. Communication on the same piece of silicon is just inherently way, way faster than going off chip and back on again. So yeah, a typical SoC is like a whole miniature computer system. It'll have CPU cores, maybe multiple types, different kinds of memory, ROM, RAM, flash, plus all the necessary input-output ports, USB, Ethernet, HDMI, whatever's needed, communication interfaces too. And a really critical part of making SoCs feasible is the use of intellectual property cores, or IP cores. These are basically pre-designed, pre-verified chunks of logic that do specific jobs, like a USB controller or a graphics processor unit. Using these pre-built blocks massively cuts down development time and risk, because you're integrating something that's already known to work. You hear terms like soft IP, hard IP, firm IP. They just refer to how flexible versus how optimized these blocks are.
Okay, so we've got the adaptable FPGAs, the super efficient ASICs, and the all-in-one SoCs, which brings us to the big question. How do you choose? It feels like this complex balancing act. Let's break down those key comparisons. Performance, power, area of the PPA trifecta, but also flexibility, cost, time to market, scaling. And maybe the trickiest one, design and verification complexity.
All right, let's tackle PPA first. For raw performance, ASICs usually win out. Because they're custom built, they can be pushed to higher clock speeds, often well into the gigahertz range for their specific task. FPGAs can also be very high performance, especially using parallelism and techniques like deep pipelining, but their actual clock speeds tend to be lower, maybe hundreds of megahertz. That reconfigurable fabric just adds some overhead. So ASICs aim for performance close to ASICs for the functions they integrate, since they often use optimized blocks, but the overall system performance depends on how well everything works together. Then power consumption. ASICs are the kings of efficiency here. Fixed, optimized circuits just don't waste much energy. FPGAs, well, they inherently consume more power. All that programmable routing burns energy, and there's more static leakage current because the fabric has to be generic. So ASICs are complex, but they use clever tricks like clock gating, turning off parts that aren't needed, and dynamic voltage and frequency scaling, DVFS, to manage power pretty effectively. And finally, area. ASICs are the smallest, designed for compactness. FPGAs are bigger because they need all that flexible logic and routing fabric. So ME&Ts are compact because they integrate so much onto one chip, saving overall system space.
That makes sense. So flexibility and time to market.
Yeah.
That sounds like a pretty clear win for FPGAs, right?
Oh, absolutely. FPGAs have a huge edge here. Rapid prototyping, much faster time to market. Yes, because there's no physical manufacturing cycle involved, or at least not in the same way. You design, you synthesize, you program the chip, done. ASICs. Completely different story. The development cycle is long, 12, maybe 18 months typically, from having a final design to actually getting working chips back. And the upfront costs, the non-recurring engineering or NRE costs, they are staggering. You're looking at millions, easily. $5 million, $10 million, sometimes more, just for the specialized masks needed to manufacture the chip. That's before you even make one. So NRE can also be very high because they're complex and integrate lots of IP, but reusing that IP helps offset some of that initial cost. But here's the flip side. If you're producing in very high volumes, millions of units, those huge NRE costs get spread out and the cost per ASIC chip becomes incredibly low, much lower than FPGAs in large volumes.
Okay, but that NRE cost and the long cycle, It leads to what seems like the scariest part. What if you get the design wrong? What happens if there's a bug?
Ah, yes. This is where the rubber really meets the road, and it's why ASIC verification is so critical. It's paramount because, as you said, ASICs cannot be reprogrammed after they're made. If you find a bug after manufacturing a functional error, your only option is a chip respin, which means going back, fixing the design, and paying for a whole new set of masks, another manufacturing run. It's incredibly expensive and time-consuming. A bad bug found late can literally kill a product, make it obsolete before it even launches, so you absolutely must perform incredibly rigorous, exhaustive verification before you commit to silicon. We use techniques like formal verification, which uses math to try and prove the design is correct, alongside massive simulations. You have to catch everything beforehand. And interestingly, SoCs often present the highest overall design complexity. Why? Because you're integrating all these different pieces, these IP blocks, often from different vendors. And many times, these IP blocks come as encrypted black boxes. You can use them, but you can't see inside them. This makes verification a huge challenge. How do you check for subtle problems inside an IP block you can't inspect? How do you ensure these different blocks interact correctly without unintended side effects? It can be a major bottleneck.
Wow, okay. Let's shift gears a bit and talk about some advanced techniques designers use to really get the most out of these complex systems, especially FPGAs and SoC. Pipelining seems like a big one.
Yes, pipelining is absolutely fundamental. It's a core technique for boosting the maximum clock frequency FMX and overall data throughput of a design. The basic idea is like an assembly line. Instead of doing one big complex calculation all at once, which takes a long time and limits your clock speed, you break it down into smaller sequential stages and you put registers, essentially small memory elements, between each stage. Each register holds the intermediate result from one stage and passes it to the next on the next clock cycle. Now, the total time for one piece of data to go through all stages, the latency actually increases. But because each stage is simpler and faster, you can clock the whole system much faster. And crucially, you can have multiple pieces of data moving through different stages of the pipeline simultaneously. So your throughput, how many results you get per second, goes way up. You're processing more data in parallel, just spread out over time.
Okay, that makes sense for speed. But more registers, doesn't that usually mean using more silicon area? Which seems like it might be a negative for FPGAs, which are already kind of large. And what about power?
This is where it gets really interesting, maybe even counterintuitive, especially for FPGAs. While you are adding registers, pipelining can actually lead to a significant reduction in dynamic power consumption, often in the range of 40%, maybe even up to 90% in some cases. How? Well, shorter logic paths between registers mean fewer glitches, those brief, unwanted signal transitions that happen as logic settles. And those glitches waste a lot of power. Pipelining smooths things out. And regarding area, FPGAs are built with these configurable logic blocks that contain both LUTs and flip-flops. It turns out designers often don't use all the available flip-flops in a block when implementing logic. So when you add registers for pipelining, you can often just utilize those existing unused flip-flops within the CLBs, meaning the area cost of adding pipeline registers can be very small, sometimes even effectively free if you're just soaking up otherwise idle resources. It's a surprisingly efficient trade-off in the FPGA world. And another good point, those high-level synthesis tools we mentioned, they often have directives or options to automatically insert pipelines. Tools like AMD's Vitis HLS or the Intel HLS compiler can analyze your code and figure out optimal pipelining strategies, making it much easier for designers to leverage this technique.
Okay, fascinating stuff on pipelining. Let's tackle another really critical and, frankly, kind of scary-sounding topic, clock domain crossing, or CDC. This happens when you have different parts of your chip running on different clocks, right? Clocks that aren't synchronized. What kind of problems does that cause if you just pass signals between them carelessly? It sounds like a recipe for disaster.
It really can be. CDC is a major source of tricky, hard-to-find bugs in complex designs. The number one problem, the one everyone worries about, is metastability. This happens right at the boundary. If a signal arrives at a flip-flop in the destination clock domain, and it's changing just as the destination clock edge arrives to capture it, the flip-flop can get confused. It might go into an unstable, indeterminate state where its output isn't clearly a 0 or a 1 for some unpredictable amount of time. Eventually, it will settle to a 0 or 1, but if that unstable state propagates downstream before settling, you get errors. Maybe incorrect data, maybe the system hangs. And you can't completely eliminate the possibility of metastability. Physics just works that way. You can only design designed to make the probability of it causing an error extremely, extremely low. So that's the big one. But there are other issues too. Simple data loss. If the source clock is much faster than the destination might just miss quick changes. And crucially, for signals wider than 1 bit like a data bus, you have data incoherency, sometimes called convergence problems. If you try to synchronize each bit of the bus independently, small timing differences mean some bits might get captured on one destination clock cycle and others on the next cycle. So the receiving side sees a combination of bits from different points in time, which is basically garbage data. Imagine getting half of a 64-bit value from cycle n and the other half from cycle n plus 1. Completely wrong. And finally, you can also get issues with glitches, those brief, spurious transitions being misinterpreted as valid data changes when they cross the clock boundary. It's a real minefield if you don't handle it carefully.
Okay, so it's clearly fraught with peril. What are the standard ways, the clever tricks that designers use to safely get signals across these clock boundaries?
There are several standard, well-understood techniques. For single-bit signals like control signals or status flags, the most common approach by far is using synchronization chains. This usually involves putting 2, sometimes 3 flip-flops in series, all clocked by the destination clock domain. The idea is that if the first flip-flop goes metastable, the second and maybe third flip-flop gives it extra time, 1 or 2 full clock cycles, to resolve to a stable state before the signal is used by the rest of the destination logic. It dramatically reduces the probability of a metastable state causing an error. Now, for multi-bit data buses, especially high-speed ones, synchronizing bit by bit is a recipe for incoherency, as we discussed. So the standard solution here is usually an asynchronous FIFO buffer. FIFO stands for first in, first out. You write data into the buffer using the source clock, and you read data out using the destination clock. The buffer decouples the two domains, but you still need to safely pass the FIFO status signals, like full or empty, and internal pointers between the domains. And for the pointers, there's a critical trick, using gray code encoding. Gray code is a special way of representing numbers where only one single bit changes between any 2 consecutive values. This is vital for the read and write pointers inside the FIFO. When these gray-coded pointers cross the clock boundary, even if there's a slight timing skew, the receiving side is much less likely to misinterpret the value because only 1 bit is changing at a time. It avoids that disastrous incoherency problem. You also see things like handshake protocols, basically, a ready valid system where the source signals it has data, valid, and the destination signals it's ready to receive, ensures both sides agree before transfer, but it adds latency. And because these CDC issues are so subtle and hard to catch with normal simulation, specialized verification techniques are absolutely essential. Static CDC analysis tools are crucial. Tools like Synopsys Spyglass CDC or Cadence Jasper Gold CDC. They analyze the design structure without running simulations, looking for places where signals cross domains without proper synchronization, or where incorrect synchronizers might be used. Formal verification is also heavily used. It employs mathematical methods to formally prove that the CDC protocols are correctly implemented and won't fail, offering much higher confidence than simulation alone. And for those huge SoCs with tons of IP blocks, you need a hierarchical verification flow. You verify the CDC handling within each IP block first, sign it off, and then create an abstract model, a sign-off abstract model or SAM for that block. Then, at the top level of the SoC, you verify the interactions between these abstract models. This makes the problem manageable and even works for those encrypted black box IPs.
Right. So it's incredibly clear when you lay it all out, like that there really isn't one single best way to build this hardware. Choosing between an FPGA, an ASIC, or an SoC, it's a really complex strategic call. It depends entirely on what the project needs, the budget, how fast you need it, and what the long-term plans are.
Exactly. And looking forward, the trend is definitely moving towards heterogeneous computing. It's less about FPGA versus ASIC versus SoC, and more about how you intelligently combine them. Modern high-end chips, especially SoCs, are increasingly mixing different types of processing elements together. You'll find dedicated ASIC blocks for super high performance, fixed tasks, maybe some FPGA fabric for flexible acceleration or adapting to new standards, plus general-purpose CPUs, GPUs, DSPs, all integrated onto a single piece of silicon or within the same package. It's about leveraging the strengths of each approach, creating a synergistic whole that's more powerful and flexible than any single approach on its own.
It really is amazing when you think about it, how this constant push for integration and combining these different approaches leads to this incredible balance. Performance, flexibility, cost, all juggled in the devices you use every day without even thinking about it. So maybe next time you use your phone or stream something or hear about a new AI breakthrough, just take a second. Think about how this relentless evolution in the underlying hardware, this clever mixing of FPGAs, ASICs, and SoCs, isn't just improving things now, it's literally paving the way for the next wave. For things like future AI, maybe quantum computing breakthroughs, even pushing further into space, it's enabling possibilities we can barely even imagine today.